Hello, stats students. We are ready to start Chapter 11, Other Chi-Square Tests. So we've got three kinds of tests we're going to do in this chapter. The first one is a test for a goodness of fit. Seems like an awkward way to say it, but chi-square statistic can be used to determine whether a frequency distribution fits a specific pattern. For example, do customers have a preference for a particular color, or are all of them preferred equally? Think cars or something. Do accidents occur only at certain intersections more often than at other ones? Or do causes of airline delays occur at different or the same rates due to, say, weather or due to mechanical issues? So we could look at those kinds of things. So a few reminders about chi-square distributions. First of all, they are based on degrees of freedom. We know that, right? Degrees of freedom change up a little bit, but we're so accustomed to them subtracting 1, n minus 1. Chi-square distributions are positively skewed. So if we're visual, a chi-square distribution looks something like that. So positively or right skewed. Our chi-square value is always greater than or equal to 0. So think about this chi-square distribution for you visual people as, say, a quadrant 1 of a coordinate plane. And last but not least, the area underneath the curve is equal to 1. So we just said that our chi-square values are always greater than or equal to 0, so starting at 0, but this shaded region is always going to equal 1. So that's a blast from the past. We talked about that back in section 7.4 and 8.5. So in order to calculate expected frequencies, so this is what we think is going to happen, and we're going to compare it to what did actually happen. So to calculate our expected frequencies, it's a pretty simple formula. E for expected equals n times p. Remember, n, is our number of observed frequencies times the probability or percentage for that category. I think I've got this wrong. Just don't write observed, the number of frequencies. We'll do an example and talk. Actually, it should be the number of total frequencies. Sorry. It must be close to the end of the school year. Number of total frequencies, or our total sample size, right? That's what we're so used to with n anyway, is our sample size. So I wanted to start by just calculating some expected frequencies. So it says to find two separate frequencies, and I made the table this way, for a sample of 175 truck colors. So n equals 175, that's our total number of frequencies. That's what we're looking at for our entire sample. So our category probability, it says in part A, the proportion of popular truck colors are white 31%, black 19%, silver 11%, red 11%, gray 10%, blue 8%, and other is 10%. So we know that this is 31% of our sample should be white. So we're going to take that and we're going to do n times p. So our sample size is n, and our probability or proportion for this particular category is 31%. So 175 times 0.31 gets us an expected value of 54.25. So we'll do that for each one of these. Black trucks are 19%, so 175 times 0.19, we get an expected number of black trucks of 33.25. I want to talk about that decimal. Silver, our expected, or our probability is 11%, so we're going to take our 175 times our 0.11, and we're going to get 19.25. Red is the same 11%, so another 19.25. Gray is, what, 10%? So 175, you can't really see when I write in yellow. 175 times 10%, so 17.5. Blue is 8%, so 175 times 0.08 gets us exactly 14, and other is 10%. Other is 10%. So that's the same as our gray, or 17.5. So I know that we can't have 17.5 trucks, but this is just like back when we talked about frequency distributions and we found means of, say, dice rolling or whatever, and it was 3.5. So it's an expected value. It's not always a whole number because remember, this is based on a sample. If we're looking at a population, we would have much larger numbers, but this is what we expect. What about if our truck colors are equally popular? This is part B. So equally popular, how many categories do we have here? We've got 7 categories. So we can common sense our way through this. We could take 100%, divide it into 7, or we can just say if we've got 175 trucks, and we're going to split that into 7 equal categories, we would expect a nice, neat 25 for each one of them. So equally probable means equal expected values. Observed frequencies will almost always differ from expected frequency due to sampling error, right? Frequencies differ from sample to sample. That's just how it is. We want the sample to represent the population, but some are better than others. Some are different because we can't get that exact perfect representation. Here's what we're doing in this whole section. We want to know if the differences between observed and expected are significant, or if it's just a chance thing. It's just a sampling error, not a big deal. So that's where we are going to perform a hypothesis test. So here we go. Let's talk about this. One of the things I wanted to do this expected frequency because that's one of the things that we need as we do our test. So we're going to do a chi-square goodness of fit. How well does our observed data fit into our expected pattern? So chi-square goodness of fit test is used to test the claim that an observed frequency distribution fits the expected distribution or the expected pattern. So observed frequencies, I've got 2 things about this. The first thing is observed as actual frequencies. So we are going to collect data. That's our data. We've observed this. Expected frequencies we need to calculate, and this is what we're going to use to test to see if our observed matches our expected or if there's a significant difference. So before we go to our 5-step procedure, let's talk about our formula. So our formula brings back some oldies. Remember, it's chi-square for our test statistic, which means we're going to use our chi-square table to find our p-value. And the formula to calculate our statistic is chi-squared is equal to the sum of our O minus E squared over our E. It's super fun to type into your calculator. So O is our observed values. E is our expected values. So if we've got a table that's 3 by 2, I've got 6 pieces of data in there for my observed, 6 calculations for my expected, 6 parts to add up for my chi-square test statistic. So we're going to do our observed value minus our expected value squared, and then divide that by our expected. Degrees of freedom in this case are the number of categories minus 1. So we're not going back to n minus 1, we're doing the number of categories. For the trucks colors that we just did, we said we split 7 categories equally. So that means our degree of freedom for the trucks would be 7 minus 1, 7 categories minus the 1. All right, so the measure of discrepancy between the observed values O and the expected values E is our chi-square test statistic. So we want to know how much of a difference it makes sense. So a couple assumptions first. So this is conditions that we would test if we were testing conditions. This is things that must be true. Try to keep it short and sweet. The first thing, I think we all know at this point that our sample needs to be random. And just a quick spot check, we need to look at our expected value table and make sure that all of our expected values are greater than or equal to 5. If not, we've got a slight problem. We probably should stop and talk about this. Our procedure for our chi-square goodness of fit test looks a lot like our procedures that we've been working on all the time. Step 1, write down our hypotheses and our claim. Step 2, let's calculate our test statistic. That is our chi-square equals the sum of our O minus E squared over E, which means that you have to find expected values before you can do that. I actually write out a little table, calculate them. You're going to be given observed values, but you're going to have to find those expected values. Step 3 is to find our p-value. We are going to our chi-square table. And I'm going to say it here instead of in step 4. This test is always one-tailed. Because remember, our chi-square values are always 0 or positive 0 on up. So we don't have to worry about alpha over 2. We're just comparing our p-value to our alpha. Sorry about that. So when we make our decision, we're going to compare our p to our alpha. Do not worry about alpha over 2. And do you want me to write down as well if p is less than or equal to alpha, reject. If p is greater than alpha, do not reject. And step 5, summarize, just like we did before. Make sure you use context. So there is enough evidence to support the claim that the expected values of truck colors are equally likely, something like that. And our hypotheses, just so we've got kind of a format to follow, our claim distribution of fill in the blank context. So thinking back to that truck example, I might say the claim distribution of truck colors as white is 31%, black is this percent, other is 10%, whatever, is true. So we always make the assumption that it is true. And I know I've got the word claimed in there, but that's what part of the data is. So that might not be our claim. Our claim could be that the claim distribution of truck colors with this information context is not true. But true is always H sub O, and not true is always H sub 1. All right, so let's do an example. I've got 2 examples. Let's do the first one, arrest for crime, because we do not have everything calculated. The second example is the truck color one. So arrest for crimes. In a certain city, the police department wants to determine whether there's a difference in the number of arrests for 4 types of crimes. So right here, whether there is a difference. So that means that H sub 1 is going to be our claim. Because our H sub O is that the claim distribution is true. A random sample of 160 arrests, so there's our N, showed 38 for larceny thefts. Let's fill this in. This is observed, right? 38 for larceny thefts, 50 for property crimes, 28 for drug use, and 44 for driving under the influence. Use alpha equals 0.05. So if there is a difference, that means that we're thinking that are expected, they're all equally likely. Equally likely. And how many categories do we have? Equals 4. If we point that out now, we can do 2 things. We can talk about our expected. We can also talk about our degree of freedom. Here is our N equals 160. So basically, I got to common sense myself through this. If there's 160 arrests and we think that they're all equally likely for the 4 different types of crime, that means I'm going to do 160 divided by 4. So I would expect to get 40 arrests for each type of crime. All right, so all that background information is done. I can also say right here that DF equals 4 categories minus 1. So when we're up to finding our p-value, we can remember that. All right, so let's start with our H sub O. So our H sub O, our claimed distribution of arrests is true. So there is no difference. I'm going to write it that way if you don't mind. How about I'll do this? Claim distribution, right? They claimed up at the top that we thought they were equally likely. Equally likely for all 4 types of crimes. Once I write this out once for H sub O, I don't necessarily need to write it out a second time. So I'm just going to say the claim distribution is not true. I'm trying to stick to my H sub O and H sub 1. But what does that mean in terms of this? Well, if the claim distribution is not true, that means that they are not equally likely. There is a difference in proportion. There is a difference for types of crime. Okay. Step 2 is to calculate. I'm going to try to save myself some space here because I got to see. Step 2 is to calculate our chi-square test statistic. So remember, chi-square is equal to the sum of all of my observed minus my expected squared over my expected. So we've got this table nice and neat here. So I've got 38 was my observed for larceny thefts, minus 40, which was my expected squared over 40. You always repeat that second number, plus 50 observed for my property crimes, but 40 expected, plus 28 observed for my drug use, again, 40 expected, plus 44 were observed for driving under the influence over my expected. So 4 pieces. If I break this down, if I did each piece individually, we could do it that way. Double check, find a way that works for you. If you want to know what each piece is, I got a 0.1 plus a 2.5. I typed the whole thing into my calculator straight across, but if you want to bit and piece it, you can certainly do that. My chi-square in the end ended up being a 6.6. The hard part's done. We just have to remember now, how do we get our p-value? Well, we said that our degree of freedom was 4 categories minus 1, so 3. I'm going to go to my chi-square table. I'm going to look at degree of freedom of 3, and I'm going to trace that across and find out where 6.6 falls in between. So here's the interesting thing. If I look for 6.6, it's falling in between, what would that be, a 0.05 and a 0.10. Remember, if it falls off the left side of the table, it's actually greater than. If it falls off the right side of the table, it's actually less than, because the p-values across the top are running in backwards order. So my p is somewhere between 0.05 and 0.1. So step 4, if I'm going to make a decision, compare my p-value somewhere between 0.05 and 0.1 to my alpha, which was a 0.05. Anything for that p has to be greater than alpha, which means that I am not going to reject H sub O. So that means for my summary, I did not reject H sub O. That means that I think that my claim distribution is true, and it is equally likely to get for all types of crimes for each to occur. So how do I write this? Step 5. What was my claim? There is enough evidence to support the claim that all 4 crimes are equally likely. This is the tricky part, to put it in all 4 types of crimes, to put it into words that make sense. Don't get too stressed about this. If I can see where you're going with it, I'm not going to get super technical, but knowing what we're looking at for our H sub 1 and our H sub O. You just have to be careful with H sub O, the claim distribution. Sometimes the airport might be claiming different reasons for delays for airplanes. And that would be the claim distribution that we would think was true. This one was thinking that all 4 types of crimes are equally likely. We'll save the other example, the truck colors, for class. This one, the p-value is interesting because it falls off the right side of the table. And that is it for section 11.1. I love doing chi-square tests. They're kind of fun and cool and different. So you do need that expected value table. Thanks so much. Have a wonderful